Hi, this lab is atomic emission spectroscopy, and I'm going to demonstrate the collection of an atomic emission spectrum. We'll also look at a continuous spectrum of light as opposed to an atomic line emission spectrum, and we'll learn a little bit about why we have a line emission spectrum. And the lab is basically about doing some calculations with that. So what are my tools that I have? Well, I've got the computer screen, which you can see, and you can see that there is what looks like a rainbow of colors, a continuous rainbow. There's no breaks from violet, actually looking at the screen, it's red, orange, yellow, green, so it's the Roy G. Biv of colors, starting from one side to the other. On this side here we have about 700 nanometers, and on this side over here we have about 400 nanometers. Now, connected to the computer is this device right here, which is called a red tide USB spectrometer. So this measures light. This is hooked up via a fiber optic cable coming out of the front of the machine, and the fiber optic cable has another end that looks like this. Now you can notice when I move this fiber optic cable, this end, something seems to happen to the spectrum as I move it around. So in this room right now I have the lights turned off, and I'm pointing the fiber cable outside the window. So you can see that depending on how I move the fiber optic cable, I can get a bigger spectrum or I can get a smaller spectrum. Now, the spectrum there that we see is light that is being emitted, so to speak. So light that's coming into the fiber optic cable from outside. We call this a continuous spectrum, and it looks like there's a lot of light in that greenish and bluish area. And I suspect that the reason that's the case is because when I'm pointing my fiber optic cable through the door, looking through the door, what I see out there is a lot of bushes. And the bushes are green, which means they're reflecting green light. And so that's why we have the high emission in the green area. Okay, so let's take a look at this fiber optic cable and see what happens if I point it at the light coming from my cell phone. So this is my cell phone. I was using it to light up the spectrometer right here, and now I'm going to point the fiber optic cable towards the white light of my phone. And if you take a look at the white light of my phone, you can see that it too is a pretty continuous spectrum. There is a couple of humps, but there is no line in there anywhere. So this light from my phone is a pretty good source of what we would consider to be white light. And if you take a look at the light, it does look rather white. Okay? All right, so that's pretty interesting. So what is a line spectrum? Well, a line spectrum is something that is emitted when you excite the atoms of an element. So if we take a look here at the lamp here to the right on the screen, I'm going to put my hand in front of the lamp so there you can see it. Now you can't see it, now you can see it. That's a neon lamp. And the neon lamp looks rather red. So here we would expect if we put the fiber optic cable and point it right here at the neon lamp, so I'm going to connect it via this little device here and put that in place. And I'm going to make a little adjustment here. So now the fiber optic cable is pointing and looking at the neon lamp. Let's take a look at this emission spectrum. Do you see that? I apologize here that the numbers are backwards. This is 700 and this is 400, and it doesn't look like 400 because it's backwards. But nonetheless, when we look at the emission spectrum, you can see not a continuous spectrum, but lines. Lines. And we have no lines in the blue or green areas, but we do have a line in the yellow, some lines in the orange, and a lot of lines in the red. Well, That's the explanation for why neon light looks red. It's emitting a lot of red light. So the neon spectrum is pretty complicated because, well, neon has a lot of electrons in it. These lines are being emitted from electrons changing from one level to another. So we have a whole lot of things going on there because we have a whole lot of different electrons and a whole lot of different levels. So let's look at something simpler. Let's look at an atom that only has one proton in it and one electron in it. That's going to simplify matters very much because we're only going to have something like 7 levels with the electron moving between those 7 levels. And when the electron goes from a higher, less stable level to a lower, more stable level, it's going to emit energy in the form of a line. Okay, so I'm going to switch this to a hydrogen lamp. So here's a hydrogen lamp. You can barely see it. It looks kind of white, maybe pinkish. And if we take a look at the spectrum, you'll notice that we only have 2 intense lines. One is in the red region, around, looks like from the numbers, around 670 or so abouts, and one in the blue region, which looks like it's around 490. Now, our book calls that blue one a green color. Based on the spectroscopy done here, it looks more like a blue color. So that blue line and that red line mixed together, making kind of a pinkish, reddish, but faint pink light that looks almost white. So that's your hydrogen spectrum. And these 2 lines are brought about from an electron going from a higher level to a lower level. When it goes from a higher, less stable level to a lower, more stable level, it releases energy. That energy is given off as light. And because the change in energy is discrete, meaning we can measure the levels, and it's a jump like a step. Every time it goes from one level to another, it emits the same amount of energy, so you get a single line or that single change in energy. So these changes in energies are going from levels like n equal 3 to n equal 2, or 4 to 2, or 5 to 2, or 6 to 2. Those are the ones that give us the visible wavelengths of light. So what happens if you go from, say, not 6 to 2, but 7 to 2? Well, it turns out that that change in energy is going to be more energetic, and so it's going to be a lower wavelength. And a lower wavelength means it's going to be in the ultraviolet region, which means we can't see it using these devices. So that's your introduction to spectroscopy. And we're going to be doing a lab based on this where we do some calculations of energies of an electron of a hydrogen atom in different levels. We're going to do some calculations so we calculate the change in energy when the electron goes from one level to another. And then we're also going to do some calculations where we calculate the wavelength we expect to see for those different levels. All right, that's it for now. Thank you for listening.